By the way, the topic itself is pretty much a mixed. I don't know how many of you would have interest in this area, but then it's talking about a technique in terms of treatment of organic waste in water. And we had a scenario in Middle East countries where they have a lot of organics coming from olive oil waste, which they want to reuse. So they have water shortage. So this was the technique which we wanted to test. And so if I take it to the next screen, there were three different aspects of this technique which are commonly used: the catalytic wet air oxidation, the homogeneous phenton, and phenton. Now, the definition of phenton is it has got some iron compounds as a catalyst. That's why it's considered as a phenton. And photophenton is because it has got a UV treatment to accelerate the process. Some of the details which are provided for the process, which has kind of set the scenarios. And then we wanted to consider saving of the wastewater, which was otherwise being dumped into either a wetland, river, or sea, so that we have equivalent costs for those treatments. The technology itself, maybe I'll just give a brief overview depending on the audience we have. So the catalytic wet air oxidation has got, of course, it has got a catalyst in it, which is ferrous nitrate. And then the temperature has to be maintained between 120 and 150 degrees. So that's a higher energy demand. And the task we were facing is how to address the higher temperature demand. And then we have photophenton, which has other energy demand for UV operation, UV lights. The UV lights, as you may know, is conventionally from mercury vapor lamps, but more and more of these are being replaced with LED, which are more energy efficient. So we tested two scenarios. And then we use some of the literature data from existing evidence in terms of energy use, so that because we were trying to develop a scenario, so we wanted to use some of the data which has already been published for similar olive wastewater treatment. And then we use some economics to do feasibility of our project. So we had capital investment because in the beginning you have to set up some kind of a reactor for these wastewater treatments. So the costs of those were considered. And then there were some operational and maintenance annual costs. And those were used to consider their feasibility for the three different techniques. The scenarios which we had was either we dump the whole of the wastewater into those three areas like sea or wetland or river, or we treat a portion of that. But then because the efficiency of these techniques are not 100%, we will still have certain portion of the effluent or the wastewater which has to be discharged. So the company will still have to bear some cost for discharging it. So that was scenario B. And then in scenario C, we had more active intervention in terms of how we reuse, the scenario D, we had more application of the kind of recovered water. So that way we are saving some of their costs. So for example, they were buying some water in terms of industrial process water, but then that could be saved by reducing their water demand. On the other hand, they were discharging or dumping some of this organic waste, and that had transport demand. So that had also been saved. So these are the few things which we considered in our modeling. And then we also had a new scenario where I think I will come to you, which is in terms of increasing the renewable energy input. Because in the end, so far what we were doing is mainly focusing on the technology, but also now we had replaced some of the energy demands for warming of the water or for using the UV or UV lights. We could replace using the renewable systems. But they also have costs, we bear that in mind. So then comes the actual output, and I don't want to give a lot of emphasis on what we are seeing here because I know I respect the diversity of the audience today. So what we were seeing is, in terms of colors, of course, the majority of cost is for discharging in wetlands, and wetlands are considered as static water. So the cost of discharging in such systems is higher compared to sea because sea gets more diluted. But then also we saw that over the period, this whole operation has got some kind of a profit or some kind of an advantage over a longer period. Then comes the actual scenario where we had full recovery of the used water, and then we realized that it starts giving profit. Yeah, so that was kind of scenario where scenario D, remember from the options. And then the one which I wanted to focus more in this session was kind of where we started using saving of the energy cost. So while we were reusing the recovered water in scenario D, in scenario E, we are also reducing the energy demands for the high temperature, because some of the processes, they have high energy demands. And if we could replace some of those conventional energy systems with the local, and in arid regions, especially in the case study scenario which we did in Jordan, there was a plenty of solar operation. So we could consider that as a replacement for energy demand. And that gave us some offset. And the offset is considered at the moment per meter cube of operation, but that could be scaled up in terms of the size of the plant. And we utilize some of those scenarios, and main energy demands were considered for, as you know, heating, pumping, UV light operations. And then we considered the maximum advantage was for this photofountain operation. So for those who are interested to know, the photofountain had the majority of efficiency. So in terms of treatment, it has more efficiency, but on the other hand, it has high energy demand. But if we could replace the energy with 100% renewable energy, then it also gives you the offset, as you can see. So it has got major advantage if you could replace the conventional energy demand. And this is the kind of kit which we developed as part of our project. So we have just a snapshot of what we used. The solars were the main input to that. Their controls, and then underneath was the actual treatment reactor for the catalytic wet oxidation, which we had installed here for the operation. It's a mobile platform for the kind of operation which we use in our scenario. I think that's what I would consider as my presentation for the day, giving us short flavor to the diverse audience. And I should acknowledge the contribution in data analysis to Ahmed Al-Zain, and then Samir Al-Namet, who actually helped to get this whole hardware set up. And of course, the support of this project came from the Royal Academy of Engineering in the UK and the Newton Fund. So thank you very much, everyone. And then if you have any question, you can send me an email or the link I will share with you. Thank you.
So wonderful presentation, sir, and very nice research work on energy. This one. Thank you. We'll get in touch. Please do share your email address out there in the chat box. We would like to get in touch with you also.
Thank you.
Yeah, we'll get connect.